So, next we will be speaking about mathematical tools that will be needed for modeling properly continuum systems. We will start with the continuum that will be deforming. So, we will consider a system that we want to model, a system that can be moving around, and a system having a state that eventually will change, because otherwise there's nothing to be modeled. We will denote by omega, generic subsystem. So it can be the whole system, it can be part of it. And omega consists of material points, which we denote by x hat. These are sort of mathematical material points, so not based on any atomic theory and being individual atomic or elementary particles, but they are points in Rn. So they're basically real. Okay, there are infinitely many, to say the least. So they form a continuum. And from that, the whole term of continuum mechanics comes. So we think material as continuous and not atomistic as it actually is. We denote with capital X the position of x hat at some reference time, t0, that we will fix. So basically we will label the material points by a coordinate or position at certain reference time that we can basically choose at our will. At some other time, t, x hat is located somewhere in space, and that position is denoted by small x, which is a function of the original position and of time. So it's a function of capital X and t. These two x's are different coordinate systems for the material. And the capital X is called material coordinate, or Lagrange coordinate in the literature. It's a coordinate system that is following the movement of the system. It follows the material, and that's why the name. So for any material point, x will be the same throughout the whole modeling. Small x is the space coordinate or Eulerian coordinate, and it's independent of the material and its movement, but it's fixed to some laboratory frame. So material can move around in the small x space. But so it's handy when we are modeling the laboratory and follow the movement of the model system within the laboratory. As the system is moving, the individual material points are moving, and they are displaced from the original position, and the displacement is an important concept, and we will denote it by u of x and t, which is simply the difference, so the spatial vector between the point of origin and the current location. And as the displacement is varying in time, the rate of change of displacement is called velocity, which is defined as a time derivative of displacement. And likewise, we could also define acceleration of the material as the second time derivative, or time derivative of the velocity, and so on. There are more things in deforming continuum than just coordinate systems and displacements. When the systems move, they don't necessarily move with constant velocity or spatially constant velocity, so they change their shape. And the change of shape is locally measured by a thing called deformation tensor, which is denoted by epsilon bar. It's a bit messy looking thing involving partial derivatives of the components of the displacement vector. It has a quadratic term which is needed for what is called large deformation, when the displacement and deformations are big enough so that they start to affect the measurement of local deformation. In many cases, the quadratic term is neglected, and we speak of models with small deformation that don't have this quadratic component, they are linear and so on. What can be seen, what can be seen easily from deformation tensor, that if the displacement is continuous in spatial dimensions, so all the material points move with same velocity or move to same distance, the body is moving as a rigid, then the deformation is zero. Also, if the body is rotating as a rigid body, deformation is zero. So there are some rigid body movements where epsilon is zero and there's no deformation. But for other types of movements, there will be deformation that is of interest, and that will arise later in the continuum mechanical models. Finally, if the continuum has some property, like the state variable, state property, this property f can also change, so it's a generic property, and the change of the property is described or defined by the material derivative, which is the partial derivative of f when f is given as a function of material derivative, of a material coordinate, Lagrange coordinate. So that is sort of the actual change of the property in actual material point. If you look the situation as independent observer in the laboratory, we will see a different change. We will see a change that appears to be in certain position, but it has two components. So it has the time derivative of f in certain position, so the actual change of f in time, and a component that depends on the velocity of the particles that are moving through the observation point. So we will see a perceived change where part of the change is due to observing different particles at different times, and these different particles have different properties in the original time. So the value of f is different in different points, and that difference is perceived as a change. So this leads to a more complicated expression when we are dealing with the laboratory coordinates. The material coordinates are sort of handy when dealing with moving bodies. now we are ready to model the change of state of a subsystem. So we have a system that has a state at individual material points. The state can change, the system can move, the system can deform. All this happen simultaneously, and these all affect to the system overall state. So if we take a subsystem omega, the system overall state is described by the integral of the state variable on omega, and its rate of change is of course the time derivative of the integral, and this time derivative then can be expressed in several ways. I guess the easiest to understand is this one, where the rate of change of the whole state is the integral of the local rate of change of state and the rate of change due to inflow and outflow of state variable or state property through the system boundary. So this refers to system boundary, and this is the normal of the system boundary. So there's something happening on the boundary that will add to what happens inside the system at given points. In material terms, in material coordinate terms, things are expressed in a bit different way, and we get a volume integral that describes the change. Deriving these is a technical exercise that will be too long for a short lecture. As we have boundary terms here, we will have to be able to cope with both volume integrals and boundary integrals, and there's a convenient mathematical tool for that called Gauss formula, which for vector f links the so-called divergence of f integrated over domain to the boundary integral of the function f or its normal component. And this will be needed when playing around with these things. So now we have the mathematical tools.